chemistry. Welcome to the synthesis of Aspirin Lab. So today there'll be a video of the synthesis of aspirin using micro-scale glassware. So what I have set up are the materials, a 4-place balance, some other labware that I'll explain in a minute, and we're primarily going to be using in organic chemistry is what's called a micro-scale glassware kit. So you can see in here that most of the glassware is smaller than my hand. So today we're just going to be using a 3 milliliter conical vial, and if you look carefully at the bottom you can see that it has kind of a V shape. And what this does, this kind of glassware, it allows us to use much smaller volumes and therefore use less materials and do things more safely. So back on the synthesis side, what we'll do, I'll first mass out the materials, add additional reactants including phosphoric acid and acetic anhydride, and then we'll come over here to our hot plate and let the reaction react for about 15 minutes. And then we'll assemble what's called a Buchner funnel. And the Buchner funnel I'll explain when we get there, but that's what we use to do the filtration. So when you're doing this lab at home with the video, you should be making sure that you record all the masses of the reactants and then later the masses of the products. So this will include massing of the empty vial, massing of the empty vial with a boiling chip, massing of the empty vial with the boiling chip, and the salicylic acid, the primary reactant. So the purpose of the boiling chip is, so when we're heating up the sample, what that does, it provides real tiny nucleation sites. The boiling chips are just small bits of carbon, and those nucleation sites provide little bitty spots for bubbles to form. So instead of getting one big bubble and the solution would bubble and pop over the top, we get a bunch of tiny bubbles, so it allows the reaction to heat in a controlled manner instead of potentially overheating or over bubbling and then losing your product or causing a big mess. So then the next series we'll start the massing and the other reactants and then start the reaction. So now we're ready to add the reactants, and the first step would be to mass the empty vial. And I'm turning on my balance to make sure it's reading 0. So the first step then would be the mass of empty vial. And that's 18.1734 grams. And now we're going to add the boiling chip, and then we'll add the salicylic acid. And we need the mass of all three of those things, so you can do the math and subtract out and obtain the mass of the reactant salicylic acid. So when I have people mass things in the lab, a key thing is to take the vial out of the balance and then add the necessary reactants. Never in the balance, because if you do it in the balance, it's much more likely that you could spill things and make a big mess. So I've added the boiling chip. Now I'll take a new mass and record that. And I'll show those numbers in a minute. So now I want to add as close to 0.15 or 150 milligrams, 0.15 grams as possible. So take it back out. I'm going to add a little bit, and add a teeny bit more, and I'm going to check to make sure that I'm close. So I want to have about 18.34 so I need a little more. It's okay to go a little over, a little under, as long as you record exactly the mass that's in there, so later you can calculate the percent yield. So now I have about 0.07. I need a lot more. Go again, and I always weigh things over a tray. You can see I'm doing this on purpose a little bit. By doing it over the tray, if I spill stuff, it's very easy to clean it up later instead of making a mess on a bench top. So now I have a little bit too much, 0.27. So I've got to take a little out. I overdid it that time. There, 0.36. So that's close enough for what we're doing. So 18.3642. So later you'll subtract out those numbers to find the exact mass of salicylic acid that was added. So here's the numbers if you want to look at them again more closely to record. And I'm going to add a few more reactants while that's showing. So then the next step was to add, now you take it back out of the balance, 300 microliters or 0.3 microliters of acetic anhydride. So I'm using an auto pipetter. It's already set to 300 microliters, if you can see that. There's the auto pipetter. So I'll add that reactant to the vial. That's all set. Put the cap back on. And then we add a catalyst, 1 drop of phosphoric acid. So all those things are what we put in the vial for our reaction. And again, hopefully you recorded those numbers. I'll show them again later as we proceed. So then we can come over to the hot plate. And I've already turned the hot plate on, so it's warming, so things will go a little quicker. And there's our reaction. We have a thermometer set up with the hot plate to monitor the reaction of the vial. So what this setup is a what's called aluminum heating block on a hot plate. And what that aluminum heating block does, it allows us a place to put the vial safely so it won't tip over quite as easily. You can see there's our reactants in there. And it also provides like a heated jacket for the flask so that it stays warm during the course of the reaction, and therefore the reaction proceeds faster or better. So what I'm going to do now is pause and come back in about 15 minutes. The video will keep going. All right, welcome back, everyone. I'm going to let this run for about 15 minutes. Reacted for about 15 minutes. And then come back and show you how to do the filtration step. The hot plate is still going. So now, if you look closely, you can see that everything has dissolved and reacted. So the next step in the procedure is to add a small amount of distilled cold water. So I'm going to move over to here. So it's a little more visible. So the point of adding the water is it's going to react with any excess acetic anhydride, and the water also makes the product more insoluble, whereas the reactants are more soluble in water. So now the goal is to cause all the product to precipitate out in a cold water bath. So I have it in the cold water bath, and what I'm going to do is add a little more water to cause all the product to precipitate out. So now, if you look close, You can see a lot of cloudiness in there, and that's all the product has started to precipitate out and settle to the bottom. So I'm going to put that back in the cold water bath and set that aside so we don't lose it. So the cold water bath has ice in there. So now I'll just let it chill. I'm going to move this out of the way while I set up the Buchner funnel filtration setup. So in a Buchner funnel filter, what this has is a side arm, and that side arm can go to a vacuum line, and I'll zoom in on that in a second. And what that does, it allows us to vacuum things, to filter them more quickly than just letting it sit there and drip, drip, drip real slow. So I'm going to hook up a hose that comes from the sink, and what the hose does, I have everything clamped so this won't tip over. So the hose connects to a vacuum sidearm setup of the sink head. So what happens when we run the water, as the water goes through this tube like it normally would for your home sink, as the water goes through this tube very fast, this tube is smaller, so because that smaller tube is there and the water is going past it very, very fast, it creates a vacuum in the orange hose that then allows the filter flask to be under vacuum. So while that's running, I know it's a little loud. I'm going to move over here back to the balance. So inside the Buchner funnel is a porous white ceramic disc. That's not the filter paper, that's very porous. It just holds the small piece of filter paper. So when we filter out the product, we need to know the mass of that paper because we want to be able to subtract that out when we're done. So now I'll go back over to the balance. And to do this, I'm going to mass out an empty beaker and then add the filter paper to it and mass it again. So I'll put over here and move my mess. So here's the mass of empty beaker. That's 29.2691. And then I add in the piece of filter paper, so I have its mass to subtract out later. So plus the paper. Now it's 29.2828. So now I can take this back over to my filter setup. Add my piece of filter paper. I'm going to save this beaker for later because I know it's mass. So when you put the paper in there, it doesn't stick very well. And if it's not sticking well, when you pour your product in, it could wash under the paper. So I'm going to add a little water, and now you can hear the water sound decreases because now it's creating a vacuum. So it sucked the liquid through really, really fast. So now I have my product vial. I'm going to use my little scopula to kind of stir it a little bit. And it doesn't seem like much, but all the product is down there in the bottom. So now that it's filtering, I'm going to go ahead and pour it through. And you can. So now that we're filtering again, you can see in the vial there's still lots of crystals. So the simple method for that is you just add a little more water and swirl it some, and you can keep rinsing it. So I'm going to add a little more water. This time I'm going to use a real small scopula to stir it up. So I want to get out even the boiling chips because some of my product could be locked into the boiling chips. So they're a little bit tricky to get out, but that's why we have the mini scopula. So again, just keep rinsing it. You can't have too much water because the product is not soluble in water, but the reactants are. So the more I dissolve the product in water, reactants in water, and wash them away, the better the purity is going to be of our end result. So I'm just going to scratch out the little boiling chips. Try to get as much product out as possible. So that's one thing when you write about your discussion of results. If the percent yield isn't very good, or it's a little low, maybe it's not 100%, hopefully it's not more than 100%, you did something wrong. But if you don't get every last little bit out, that's part of what our problem is, that some of the product was still stuck in the vial. So now what I'm going to do is just let the water run for a few minutes. And what that does, it allows the sample to air dry as much as possible, because the vacuum is just going to suck air through the Buechner funnel. So the drier it is, that means it'll be easier to get out of the Buechner funnel. It won't be dry enough to mask right at this moment, but what I'm going to do is I'm going to let it dry and then come back and record the final mask and show you that. So I'm going to let this air dry some. Alright, so when it comes time for doing the actual lab report, if you look in the handout explains all the details for the format, the page size, the margin size, the font size, and all the headings and sections to include, and there's instructions as well. So for you, for the procedure, you can greatly summarize what's written there, just to at least highlight which major steps were done, and in the report you can talk about the reactants and the products and the materials and how they were set up and used, and again greatly abbreviate what I provided for you. So it's not meant to be a word-for-word verbatim modification of what's there, but just an abbreviation. Alright, so I'm going to assume this is dry enough. So when you use a Buechner funnel, it's under vacuum, and what that means is any liquid down here is also under vacuum. And what tends to be a better approach for getting your sample out of the funnel before you turn the water off would be to loosen the funnel. Now you can hear the vacuum being drawn, and then turn the water off. So what that does, if you turn off the water with the funnel still on there, the vacuum could cause a big surge of air that splashes water back up into here and then causes your product maybe to get lost. So now all you have to do is tap it into your pre-masked beaker, and you can see in there I got everything out, even the little bit of filter paper, and it's not dry enough yet, as in there's still some moisture in there. So we have to let this dry for a little bit, and I'm going to report back to you on the next step what the final mass of the product is. So we'll come back in a bit, well I will, and the video will keep going with masking the product and then doing melting points. Alright, so here we are again with the product in the pre-masked beaker, and we can see now that the total mass of the pre-masked beaker plus the filter paper plus the boiling chips is about 24.40. I should close the door. I'm going to say 6.9 because that's what I first wrote down. So now you can see here's all the data that eventually you'd have to record on your lab sheet and then in the report. So again, key parts are, to get the mass of the product, you have to subtract out the mass of the empty beaker and the paper, and then subtract out the mass of the empty vial minus the boiling chip. So what that'll give you is the boiling chip mass is about 0.02 grams. So 29.4069 minus about 0.02 minus the mass of the paper will give you the mass of the final product. So you want just the mass of final product to then do stoichiometry and calculate the percent yield based on the initial mass of salicylic acid. So if you have questions on this math, please feel welcome to ask, and I'll make sure you're doing the subtractions correctly. But the key thing is I want you to be able to do the percent yield calculation. So next I'm going to come over and show you the setup for doing melting point. So here we have what's called a melt temp or melting point apparatus. And what this does is you can put a sample in there and watch for it to start melting and record the melting point. So to prepare your sample for this, we just use, I have little bottles of these tiny glass capillaries. So these tiny glass capillaries, all we have to do is take our product, the seal salicylic acid, and all I'm doing is just tapping a little bit in, and you can see maybe there's a tiny bit in the vial, the capillary, and I tap it on the bench top until it falls to the bottom of the capillary. So now I'm going to add a little more, and then inside the melting point apparatus there's a little window and a rectangular groove that window looks into. So I'm going to put the capillary in that little rectangular groove, and when I turn on the instrument, now it lights up. I'll move the capillary in and out so you can see where it's going, hopefully. And that little lens there is what we'll look in to watch for it to melt. And it's probably going to be pretty hard to catch this on the camera, but I'm going to talk you through it. So to measure the temperature, we of course need a regular thermometer. So I'm going to have the thermometer in there, and then we turn the setting up so that it starts heating up. So this part can take about 10 or 15 minutes for it to heat up and the melting to occur. So I'm not going to run the video for 10 or 15 minutes. But again, I'll zoom out so you can see a better shot of the melting point apparatus and the whole setup. So again, what we'll do, I'll do 3 trials of this and provide the data for you in a few minutes. Welcome back, of sorts. Alright, so I've done 3 melting points, 3 trials, and I'll provide a summary of the data at the end that's typed, and therefore you can record it for your report's sake. So here are my 3 melting point ranges. So when you record the melting point, you simply watch and watch and watch and watch for it to melt, and ideally at the end all the solids go away. So I'm real close right now to having one more melt, and that's what I was going to show you as it melted, the end result. So my 3 melting points I got were listed there. For you in the report, what you should do is report the average of the left side and right side to give you an average range. But then when you go calculate the percent error, you can take the average of the average 2 numbers, but then you have to compare that to a known value, which you have to look up, so you can compare your experimental value to the theoretical value. And I'm waiting here to see if it melts so I can show you. It says we're at about 128, so we're close. So I'm going to try to zoom in on the little lens in there. I don't know if it's going to come up in the video, but ideally we should see the little capillary in there. I'm waiting. Should be melting any second now. And after this, I'll pause the video and then restart with the acquisition of an FTIR or infrared spectrum. And we'll learn about infrared spectroscopy either about the time you're watching this video or very soon thereafter. Look in here and see if it melted. Almost. It should be right about there. I can't see it with the camera in the way, so yeah, now I can see that it's melted, and I'll put it back in case you can see it in there, and I'll take it back out. So if you look carefully, you can see that now it's melted instead of a solid. And once it cools off, of course, it'll become a solid again. So what's important about melting point is that you can use that as part of your organic unknown determination. So if you had a sample that melted at 80 degrees Celsius, you would know that it's not acetylsalicylic acid. Whereas if you had something that melted very close to that, you have a pretty good inference that I may have acetylsalicylic acid because the melting points match up. But other tests would be necessary to validate that it is indeed acetylsalicylic acid. So that's where we'll go to next with the FTIR spectrometer. Next in the experiment would be to acquire an FTIR spectrum of our sample. What we have here is our Fourier transform infrared spectrometer, or FTIR for short. And right now I don't have the sample device in there just to show you some of the optics. So on the left and the right are the input and output optics through which the IR radiation passes. And because this uses IR radiation, it has to have the ability to transmit IR radiation through the optics, which means in our case the optics are made of salts. So potassium bromide is a pretty common salt used in the windows. We can also use sodium chloride windows to make essentially a sandwich of our samples and then acquire the infrared spectrum of the liquid sample sandwiched between the samples. If we wanted to acquire a spectrum of a solid, that can be trickier. So what I have on here now is what's called a diamond-tipped attenuated total reflectance probe. So what this has, the diamond tip, it allows you to put a very small amount of sample on the tip of a diamond, and what happens is as the radiation comes through the instrument, it gets reflected up to the diamond, then the sample light reflects through the tip of the diamond and interacts with the sample over here, and then it scatters back towards the detector and goes on to the detector, and you can acquire a spectrum that way. So what's cool with this feature is you could actually have a single hair and measure the properties of a single hair on the tip of that diamond probe. So what I'm doing in the instrument with the software, we first acquire a background. So I have that started, and depending on our sample type, we would acquire many background spectra or as few as 16. So the advantage to acquiring more is over time the more acquisitions get averaged out and you get what's called a better signal to noise ratio. So while this background acquires, we'll learn more about IR spectroscopy over the next few weeks. The basics of it are is that as you pass IR radiation through a molecule or organic molecule, since we're in organic chemistry, is some of that light is going to be interacting with the normal bond energies or bonds within a molecule. So if you think about an OH bond versus a CH bond, they have different bond energies, so they'll absorb IR radiation in different locations. CHs will be different than OHs or N or other ones. So now we have our background on there. I'm going to hide a an old background. So in the background, we see a lot of peaks, and that most of these peaks come from, on the left side, are from OH from water, and over here are more OH peaks from water, and then in the middle here are some C double bond O peaks from CO2 in the air. So the molecules have to have a certain degree of polarity to be IR active. And if you really wanted to make a much neater, prettier spectrum, you could purge the instrument with nitrogen gas, because nitrogen is IR inactive. So purging it would get rid of all the moisture and CO2 from the air that's part of the sample chamber. So now what I'm going to do is I'm going to add a small amount of our sample to the diamond tip and prepare it for taking a sample reading. So you don't need much. I'm going to put a lot more on there than we need, just simply because we have a lot. We'll come back over there and show that while I'm not in the way. So now we have our sample on essentially where the diamond tip surface is. And the next step then would be just to, there's a tip you can put on there real tight, so you compress the sample tightly against the diamond tip. So now what happens is, when I come over here to collect the sample spectrum in the experiment setup, it's configured to collect a background every couple hours. So what will happen is this background should get subtracted out, and all we'll have resulting is just a spectrum of our product, acetylsalicylic acid. So now what it's doing is acquiring 32 scans, and it's subtracted out the background, and we can see a whole variety of peaks that are coming up. So what I'm going to do for you is, I'm going to have a copy of this spectrum in the actual lab handout that goes with the experiment, so you can refer to it for data acquisition. What I wanted to do was at least show you how the instrument works and how we acquire the spectrum and what you can do with the data. So again, we'll learn a lot more about IR spectroscopy in the class, and in due time, looking at a spectrum like this, you'll instantly know what kind of compound it might be or might not be. So now that it's done, I can just say yes, add to the window. What I'll do is I'll click on the background one and hide that. So again, we can see in here a lot of what are called CH peaks around 2000 to 3000. We have C double bond O peaks, and then of course down below we have the carbonyl peaks, and over here we have aromatic peaks. So all those things, all these peak locations will tell you more about what kind of functional group is present. So to back up a little bit, if you were to acquire a spectrum with nothing in there, so if I just did my background sample minus my background sample, we would get 100% transmittance of light. So what happens in the IR spectrometer, if there's a molecule there with a specific bond group that absorbs that radiation, instead of being 100% transmittance of light, we might get, in this case, about 20% transmittance of light. So what that means is this peak here comes from a C double bond O, a carbonyl. So carbonyls greatly absorb the IR radiation, whereas on this side the CHs aren't quite as strongly absorbing of the IR radiation. So again, if it was 100% transmittant, that just means all the light's passing through. If there's a low percent transmittance, that means the bond is acting like a filter to absorb that IR radiation to give us the resulting spectrum. So other samples, if we had an alcohol, they would have big peaks out here around 3600. We'll see those later. We'll see more about carbonyls and alkenes and alkynes. And again, in a short amount of time in the course, you'll be able to look at pretty much any organic molecule spectrum, and within about 3 seconds know what kind of functional group is present in that molecule. And that's going to be the key utility for us when we do IR spectroscopy. So for sample cleanup in this case, this one's pretty easy because the diamond-tipped probe is pretty safe to work with. You shouldn't scratch it too easily. We can really just wipe the sample off and then clean the diamond tip with some organic solvent. So I'm just going to recollect it to the vial, so if I wanted to use it for some melting points later, I could. If we were doing a different sample interface. I'll go back to the main chamber. If we did a different sample interface in here, now it's a little bit trickier to clean it because I don't want to get any water in there, and that's because, again, water would dissolve the organic, or it would dissolve the salt optics, and that would pretty much ruin the instrument. So next I'm going to show the data, a summary sheet of the data that you should make sure you record for doing your calculations in your report.